So, in field science in general, and archaeology in particular, we frequently use the universal, transverse, Mercator coordinate system and corresponding projections to locate where we are and where sites are and where other kinds of features are that we need to map or that we need to find. Consequently, you need to understand how the system works, and you need to be able to calculate the UTM coordinates of a site or a point or other feature from a map. For example, on the state site file site forms, right? If you find a site and you need to fill out a site form to register the site with the state, which is a routine and typical task that field archaeologists need to do, you need to put down on the form the UTM coordinates. So how do you find the UTM coordinates, right? Or if you have a site form from the state and you need to relocate that site because it's in your project area, the site form gives you the UTM coordinates, and you need to take a map and go walk to the site. How do you do that, right? How do you figure out where a point is on a map if all you have are the UTM coordinates, right? The reason that people use the UTM system for this instead of, let's say, latitude and longitude is that on maps that are drawn with the projections that are typically used, it's hard to figure out where latitude and longitude are. Unlike, say, marine navigation maps or aeronautic navigation maps, in which possibly, latitude and longitude are used more. The UTM system offers a number of advantages on the kinds of maps we use, and consequently, those systems are marked on the maps, and they're just easier to implement on the maps. It's easier to figure out where you are or to locate a point using UTM coordinates on a flat map than it is to deal with latitude and longitude, which tend to be kind of oddly curved lines on most of the map projections that are convenient to use for other reasons, right? So at any rate, it's something that you definitely need to know how to do if you're going to be an archaeologist or any kind of field scientist, and it's useful for other purposes as well. I mean, if you just like hiking, and you get the high quality government map to figure out where you're going in the woods, it's useful to know, it's really necessary to know the UTM system. I know you may think, well, all of this has been replaced by, GPSs and pads, and stuff like that. And, that is sort of happening. I'm not certain whether we'll ever completely replace paper maps with various kinds of electronics in the field. I know we see that on science fiction shows all the time. It may eventually happen, but it hasn't happened yet. And most archaeologists do not operate with very expensive pads with highly accurate and detailed maps on them. Some do, but most don't. Okay? So, follow along. There's a slide called Universal Transverse Mercator, right? And as it explains on that slide, the Universal Transverse Mercator coordinate system is based on a group of 60 cylindrical secant projections that divide up most of the surface of the Earth into 6-degree wide longitudinal strips, right? So they go down this way, right? From 84 degrees north to 80 degrees south. So it doesn't include the poles themselves. And those 6-degree wide strips are called zones, and they are numbered, right? Zone 1 is around the international date line in the Pacific, around 180 degrees west longitude, and they move, the numbers go up as they move east until you go around the whole globe. And since they're 6 degrees wide, and there are 60 of them, they cover all 360 degrees of longitude, right? These are conformal projections, which means that the angles and shapes are preserved, but scale and area are not, and they can be significantly distorted. If you have two maps, and this has happened to me, if you have two maps, and one map ends on one margin at one UTM zone, and the next map picks up at the beginning of a different UTM zone, those maps don't match up. You know, the lines that are supposed to be continuous don't cross, you know, they don't follow each other, they don't meet up. So there are significant distortions as you get away from the most accurate part of the projections, right? Now, in the UTM system, there are also a series of sort of latitudinal divisions that run east-west that are designated with letters. I'm going to show you a map of this in a second, or actually the next two slides show you maps of these things, right? The projection is secant by a small factor, just slightly less than 1, along the central meridian, meaning that the cylinder, the imaginary cylinder for that particular north-south strip of 6 degrees longitude, or 6 degrees longitude wide, actually passes, you know, under the central meridian by a little bit, right? Those tangent lines where the secant comes in and then comes out again are about 180 kilometers apart. The Universal Transverse Mercator system is used not only in the United States, it's represented on virtually all United States government maps, which is why you need to know it, but it's used very widely around the world. I've used it in every country I've worked in, and it's used in many, many countries around the world. Because it's, you know, it has some nice characteristics, and it's been extended to the whole world, and so it's convenient to use. So it's marked very clearly on the national maps of many different countries, right? So if you go to the next slide, which is also entitled Universal Transverse Mercator, you'll see that there's a map of the world showing the north-south 6 degree wide strips. And the one on the very far left is shown as 01W, meaning 1 west. I don't know why they have the W, because they're all west. But you can see that these strips go from 01 on the left to 60 on the right. And then they meet up in the Pacific along the international date line there, right? You can see that New York, or New York City, is in zone 18. And you can also see that there are horizontal, I think they're, I don't know, 8 or 10 degree wide horizontal latitudinal strips that run parallel to the equator. And those have letters, right? They start at C at the bottom and they go up to, I guess, X at the top. I've never worked that far north in the Arctic, so I'm not sure. But we don't often use those letters. So don't focus on them, but occasionally they will pop up in mapping data. You should know what they are. But I'm not going to ask you about them like on a quiz or a test in this class, because they don't arise very often. On the next slide, which is called UTM Zones, there's another map showing the zones, which just may be a little bit clearer, but it's the same map, different colors, but it's the same system. And you can see how the zones run from 1 in the west all around the globe to 60 in the east on this map. And you can also see the letter designations for the horizontal strips that are sometimes used. So what zone are we in? Can you tell what zone we are in? We're in zone 17, just like New York City, actually. On the next slide, which the title is Each UTM Zone. This is kind of the anatomy of a UTM zone, right? There's a central meridian, which is, since there's 6 degrees of longitude wide, the central meridian is 3 degrees from each edge, right? And obviously, because we're dealing with a globe or a sphere, right, the lines of longitude forming the edges get closer as you go further north, and they get closer as you go further south, and it's widest at the equator, right? Within each UTM zone, there is a set of coordinates in meters that allow you to identify your location or the location of any object, right? By using an easting, right? So you can specify X number of meters east and Y number of meters north. So it operates like the XY coordinates on a regular mathematical graph, like a Cartesian graph, right? Except instead of X and Y, you have the easting and the northing in meters, right? Now, each UTM zone is split into 2 halves, right? There's a northern half and a southern half. For the northern half, you know, the northing of the equator is 0. And then as you move north, the northing increases up to, I don't know, 80 million meters or something like that, or 8 million meters, 9 million meters, something like that, right? The distance from the equator to the pole is about 10 million meters. In fact, that's how they calculated the size of the meter, was based on the Earth, right? The easting is a little bit different. Rather than having the eastings start at 0 along the eastern edge of the zone, which would not work out because the eastern edge is a curve, so it's kind of weird and complicated. What they've done is they've arbitrarily, in a sense, decided that the central meridian of the zone, which is a straight line, is going to be not 0, but 500,000 meters east. We're going to call the central meridian 500,000 meters east. One reason that they did that was so that you don't have any negative numbers, right? Because, people make a lot more mistakes when they're working with negative numbers. So this ensures that all of the easting coordinates are positive, right? In order to ensure that all the UTM coordinates in the southern hemisphere are positive, they assign a 10 million meter false northing for anything south of the equator. So when you specify your UTM zone, you not only have to specify which of the 60 zones you're in, you also have to say whether you're in the northern hemisphere or the southern hemisphere, because the coordinates can overlap, right? So I haven't worked in the southern hemisphere, but we have people here in our department who work in the southern hemisphere. So you have to know how to use you should know how to use the UTM system in the southern hemisphere as well. Just bear in mind that, the numbers start at 10 million in the south, right? So that you don't have any negative numbers. Okay? Now, the United States government maps that we use commonly for field work in the United States show the UTM coordinate system. And the next thing I want to do is show you how to calculate your location in the UTM coordinate system on these United States Geological Survey government maps. Okay?